Good morning, guys. Let me know if you can hear me well. Can you hear me well?
Yes.
Yes.
Thank you. So what is it, Friday? Friday, September 18th. So we are almost a month into the semester. And we are working on chapter 4, three-dimensional structure of proteins. And we have been discussing secondary structure so far. So today we'll move on to tertiary structure of proteins, right? So secondary structure, remember it was basically just short segments such as alpha helices, beta sheets, right? Beta turns, some short segments in proteins. And the the tertiary structure will be on a much larger scale. So we're going to look at much larger segments of proteins, and specifically what we will see, especially with globular proteins, is that these short sequences of secondary structures, they're arranged relative to each other, right? And we'll talk about these arrangements. All right, so you've been doing suppling, right? Any questions about anything so far? Practice test, yeah?
I had a quick question about what was the random coil again?
Random coil, basically no particular no particular secondary structure.
Okay.
Right, so usually basically it's some kind of a bridge between secondary structures.
Okay.
So when the two secondary structures are packed in a protein and then they have to be connected, so they're usually connected by a random coil.
Perfect, thank you.
All right, anything else? Okay, so we will start sharing screen. Start sharing screen. So remember, just to remind you, so here we have alpha helix, right? Alpha helix, where we have the N+4 hydrogen bond for every amino acid, keeps it very strong.
Could you actually, could you go over the N+4 thing one more time?
What about it?
I guess exactly how it works and how we use it to determine. Because a few practice problems that we did on Wednesday that I was a little lost on how we were determining it.
Well, take the NH of one amino acid, then count 4 amino acids ahead. So it will be one amino acid 1, and the next one will be amino acid 5, right? And that will be the carbonyl of the amino acid 5, which forms a hydrogen bond. And so for each amino acid, N+4 stays the same, right? So 1, 5, 2, 6, 3, 7. So basically, amino acid 3 will hydrogen bond with amino acid 7. Okay.
Oh, I see now. Thank you.
Yeah. All right. So this is alpha helix. So we talked about various factors which will stabilize, destabilize alpha helix. We talked about parallel, anti-parallel beta sheets. Right. I told you that anti-parallel is somewhat stronger because of the nature of the hydrogen bond. It's straight between the 3 atoms, right? Beta turns, so we talked about that, and that's where we ended, where we have proline isomers, and we discussed the fact that 6% of all prolines in proteins are in a cis. Well, it's not really conformation configuration. So remember, conformation is something that molecules can adopt through free rotation about single bonds. Configuration is that something molecules can adopt and get frozen, like such as cis and trans, right? So here it's kind of halfway in between. So nobody really knows whether to call this a conformation or configuration, because the double bond has a partial double bond. This bond has a partial double bond character, right? So it's somewhere in between a single and double. So it's not really clear if it's conformation or configuration. Since it actually requires an enzyme to go from one to the other, I would prefer to call this a configuration, right? So it cannot basically freely rotate between trans and cis. Configuration. Now, something very quickly, now there is various ways to determine protein tertiary structure or segments of secondary structure. So we'll talk more about, maybe on Monday, we'll talk about X-ray, we'll talk about NMR, nuclear magnetic resonance. A sort of a classical method to determine if you have an alpha helix or beta sheet is known as circular dichroism, CD. Basically here you're dealing with the physical phenomenon of circularly polarized light, right? So you remember light can be polarized, can be plane polarized, we talked about in organic chemistry too, can be circularly polarized. If you want to learn more about the nature of this polarization, can, I'm sure, go to Wikipedia. Basically, it's just light rotates in alpha helix pattern. And so here we have an extinction coefficient. So this is left polarized light, left circularly polarized light, and right circularly polarized light. And it turns out that their difference depends on the secondary structure in proteins. And it's quite reliable. So let's look at that. So here you can see this is the difference between these left and right circularly polarized light, right? And you can see for alpha helix, you will see some kind of this curve where it starts up there in the positive region, crosses the 0, goes to the negative region around 210 nanometers, and then flattens out around 240 nanometers. For beta conformation, similar pattern, but a little flatter, right? And the random coil, totally different. You can see it starts even actually in negative region and then goes to 0 again. So you can use this CD spectrum roughly to predict which kind of secondary structure you're dealing with. One thing to keep in mind is that if you have a protein that has a number of such secondary structures, then the actual CD spectrum will be much more complex, right? So you'll have a contribution from alpha helix, you'll have a contribution from beta conformation, and the actual curves will not look that simple. But they will for short proteins, for peptides, for example, right? So if you have a alpha helical peptide, then you will probably obtain this kind of curve. And then you can say with 99% guarantee that actually that this is the secondary structure which has been adopted by this protein.
So basically, what this is telling us that alpha helix will rotate more light than the others.
So for the reasons are not clear. So originally it was just an experimental observation, and even now there are theoreticians who are trying to understand why the curves look the way they do. I don't know if there is a clear explanation for that. Originally, as I said, it was just experimental observation. So one thing to keep in mind is that the reason why we see these kind of responses, right? So for the left and right polarized light is because the proteins are chiral, right? Remember, we're dealing with L amino acids only, or D amino acids, depending on your system. Remember, the amino group is always on the left, in the L amino acids. R group here, L amino acid. And so L amino acids, since they are present in one enantiomeric form only, they will interact differently with the left polarized light or the right polarized light, circular polarized light, right? And so they will absorb these two sources of light to a different extent. And the difference in their absorption obviously is based on the chiral nature of the protein, but also depends on the secondary structure. So the difference will also depend on the secondary structure, how these L amino acids pack themselves into a shorter segments of proteins. So that's, I mean, I just explained to you where it's coming from, but the reason for why the curves have specific shapes that I don't know if it's still a subject for a lot of studies by theoreticians who are actually trying to understand why that is.
So you said that it could be used to determine secondary structure. How, using that graph, would we be able to use to determine it? Would like one be higher than the other?
Well, I mean, they have characteristic shapes, right?
Oh, so only one of those would be actually shown. It wouldn't all be all of them.
Yeah. So, right, so that's what I said, that in the bigger protein, when you have a number of these conformations present, then the curve will actually have much more complex character. So it's going to be more difficult. If you only have one type of secondary structure, then it's pretty straightforward. It goes straight down into negative, stays in the negative, and then zero, and goes to zero. Here it goes slightly up around 200 nanometers, goes down, crosses zero, doesn't spend much time in the negative, and goes back to zero. Yeah, so basically the shape of these curves will allow you to predict the secondary structure if the secondary structure is the predominant structure in the entire protein. Okay. All right. So tertiary structure. So now we're dealing with the overall spatial arrangement of atoms in the protein, right? It's not just short segments. Now we're dealing with overall structure, specifically how these short segments actually interact with each other and how they're positioned relative to each other. So they stabilized by numerous weak interactions, right? Largely hydrophobic. Remember, inside the protein, we have mostly hydrophobic amino acids. If you have polar interactions, there are not so many of those, but if you do have them, they're stronger. And they're stronger. Remember why the salt bridges are stronger within the protein than on the outside of the protein? Who remembers? The salt bridge, if you have it within the protein, on the interior surface of the protein.
There's no water.
So what does the water do?
The hydrophobic effect.
Remember a term known as dielectric constant, right? So water, so if the salt bridge, basically it's the interaction of the electric fields between negatively charged and positively charged species, then water will break it up because it has a large dielectric constant. Within the protein, where you have mostly hydrophobic residues, almost like in a vacuum, right? These hydrophobic residues do not interact with the electric field. And so the electric fields have a very strong interaction in vacuum because the dielectric constant is very low, close to zero. And also these secondary structures can be stabilized by disulfide bonds. So we'll talk about in a moment. And so there are two major classes of such proteins. We'll talk about fibrous and we'll talk about globular. Okay. So we will see that primarily the fibrous proteins are primarily evolved for strength. And they usually have one type of secondary structure, right? So fibrous proteins are actually simpler than globular because they have one type of secondary structure throughout the entire protein. So it's almost like their secondary and their tertiary structures are almost the same. And globular, so these will be water soluble. Many of these are enzymes. And they have multiple types of secondary structures. All right, so fibrous proteins, we'll start with those. So we'll talk about keratin. Now it's present in hair, feathers, nails, claws, hooves, horns, anything that requires strength. Now there is a, and these are based on alpha helices and they cross-linked by disulfide bonds. Then, for example, proteins, spider web, right? So these are based on beta conformation, also very strong. Remember, hydrogen bonds are involved. And silk fibrin is one of the such proteins. And we'll talk about collagen triple helix. So this is a type of secondary structure we haven't seen before, but shares a lot of common features with the alpha helices that we've talked about. And so that this is collagen. So here, tendon, bone matrix, right? Basically all the connective tissue in the body. So we'll start with the keratin. So this is cross-section of a hair, right? So these are different cells, okay? And you can see, so keratin is the type of protein that belongs to intermediate, so keratin, belongs to intermediate filament proteins. It's the type of family. Proteins. Okay. And so what's important here is a two-chain coiled coil. So what does this mean? So we have one alpha helix, right? And it's right-handed. So if you go in this direction or that direction, doesn't matter. It's the rotation of the turn is clockwise. Clockwise. So it's a right hand. So the actual alpha helix is right-handed, but the way actually they turn around each other is in a left-handed fashion. Okay, so let's see how the best to write this down. So pairs of right-handed did I put the right H correctly? right-handed helices interwound, that's the word I was looking for, interwound in left-handed sense. And so so these will be, we call them two-chain coiled coil, right? So they coil by themselves. There are these alpha helices, and they're also coiled around each other. So then these aggregate, so they basically form a number of such strings that are bound together. They form protofilaments. Then more of them form what's known as protofibrils, and then eventually intermediate filaments. And this obviously gives a lot of strength to the structures. And one other thing to keep in mind is about disulfide bond. So so in rhinoceros, for example, in the rhinoceros horn, in the rhino horn, I guess 18%. Which amino acid forms the disulfide linkages?
Cysteine.
Yeah, cysteine. 18% of all cysteines form RSSR, right? So try to spread them apart. The horn is very strong. And these disulfide linkages are also involved in, for example, in chemistry of permanent waving, right? So remember the way you do it. Now I don't do it very often. I don't know if I've ever done it, but people tell me first you apply a reducing solution, right? What does that do? It breaks the disulfide linkages. You've broken the disulfide linkages, apply heat. By applying heat, then these can shift relative to each other, right? So which will allow for the hair to bend, And then when you apply the solution, you reoxidize them, and they will be reoxidized in different positions. So different sulfurs will form disulfide linkages, and this will form a covalent bond. So this will be permanent, right? That's why it's called permanent waving, is that to unwave, you need to apply the reducing solution, heat, and put it in the right hairstyle, the way you want it to look like, and then reoxidize, right? So you can shift these disulfide linkages relative to each other, right? Just apply a reducing agent and heat. Okay. And one other thing I need to mention here, where the two right-handed helices interact on the inner surface, there'll be lots of hydrophobic amino acids. So alpha keratin is rich in, for example, alanine, valine, leucine, phenylalanine, and so on and so forth. And that's because of the interaction between the two coiled coils. All right, so that's alpha keratin. So the next protein we're going to look at is collagen. So important constituent of connective tissue, tendons, cartilage, bones, cornea of the eye. So each collagen chain is a long glycine and proline-rich left-handed helix. And 3 collagen chains intertwine into right-handed superhelical triple helix. So let's see what that looks like. It's right here. So you can see now we have a left-handed helix, right? You can see if you go in this direction of propagation, it's going to be counterclockwise turn, counterclockwise turn. That's why it's left-handed helix. And it's a repeat of 3 amino acids. So you have glycine, and then X and Y. X and Y could be anything, but in majority of cases, this will be proline. And this one will be 4-hydroxyproline. 4-hydroxyproline, we'll look in the structure in a moment. You already seen the structure actually, but we're gonna see it again. And so these are interwound around each other, right? So the 3 left-handed helices interwound in a right-handed sense. So this is right-handed. Right-handed. So we'll just call right-handed twist. And so why do we need this hydroxyproline? Let's look at the next slide. So 4-hydroxyproline and collagen. So basically it forces the proline ring into a favorable pucker, right? So basically this 5-member chain can actually adopt different conformations, okay? And it also offers more hydrogen bonds between the 3 strands of collagen, right? So if you have a hydroxy group, obviously it's capable of hydrogen bonding. And there is a post-translational modification. Remember I told you? So this occurs after the protein has been synthesized on the ribosomes. And there are several components required for this. So the enzyme that is needed is prolyl hydrolase and requires some other starting materials, alpha-ketoglutarate, molecular oxygen to oxidized, and vitamin C, ascorbate. So what is scurvy? So you know the disease scurvy. What causes it?
It's a vitamin C deficiency.
Vitamin C deficiency. What are the symptoms?
Isn't it like soreness throughout the body
Like soreness,
and muscles
probably more than just soreness, right?
and like fatigue, tiredness?
Fatigue, tiredness, we can survive, but it's a fatal disease, right? So what do you die of? So how about things like bleeding gums? How about things like hemorrhages throughout the body. Due to fragile blood vessels. How about like things like tooth loss? So what do you think could cause all of these? What's involved? What protein is involved in providing support?
Collagen.
Collagen, right. So defective collagen. Defective collagen, and it turns out that this 4-hydroxyproline collagen is just not strong enough without it. Defective collagen. So let's look at this structure. So remember, endo from organic chemistry means on the same side. Endo. And this one is exo. On the opposite sides, exo. So it turns out that for strength, the collagen proline residues want to adopt this kind of exo conformation, and the hydroxy group, which will be involved in hydrogen bonding with something else, will make this 5-member train pucker in the right direction, okay, to achieve this exo orientation. And so what does this ascorbic acid do? So ascorbic acid and vitamin C is the same thing, right? Vitamin C. Vitamin C. So here's we have our proline. Here's ketoglutarate, oxygen, and iron. So basically this carbon here undergoes oxidation with the insertion of the hydroxy group. Ketoglutarate is reduced to succinate. And one thing that is actually what we need to show, which is not shown, is oxidation of iron to iron 3+. But then, so for this reaction, we need iron 2+, right? And what happens in the next step, more of the ketoglutarate and oxygen in the presence of ascorbate. Ascorbate is a reducing agent. Now, instead of iron 2+, we have actually iron 3+ coming in, undergoes reduction and regeneration, iron 2+. Right, so ascorbic acid is crucial because of the iron chemistry. It allows you to restore the iron 2+ state so that the enzyme is ready for the next reaction cycle. Okay, so now obviously on exam, I don't want you to memorize all the structures, but I want you to know that it is the chemistry of iron, specifically oxidation and reduction between iron 2+ and iron 3+, which is where the ascorbic acid or vitamin C is necessary. So this will be oxidation, oxygen, and this will be vitamin C, which is the reduction. Okay, any questions? All right, so that's vitamin C. And collagen forms, so besides these secondary structures, it does, so these segments of secondary structure do interact with each other. There's a lot of cross-linking involved. They form collagen fibrils, and these fibrils are stronger than metal wires, right? So extremely strong. And there's a lot of hydrogen, a lot of cross-linking involved, right? So there are other types of cross-links, which we haven't discussed in this lecture, but I will give you some pages to read. There is actually one important, besides the disulfide linkages, there are other types of cross-links present in collagen, would be useful for us to know. And silk fibrin, so all we need to know is that it's an anti-parallel beta sheet structure. It's extremely strong. It's extremely strong because first of all, remember alpha helix is stretchable. Now I'm not gonna write this down, but keep this in mind. So alpha helix is stretchable. Beta sheet is not, right? Because beta sheet, basically you can't pull the hydrogen bonds away from each other. With the alpha helix, you have a spiral, so you can stretch the spiral. With the beta sheet, you're already limited by these hydrogen bonds. If you try to stretch the beta sheet, the two sheets coming together through hydrogen bonds, you will break the hydrogen bond. For that reason, for example, the spider web is not stretchable. And because it's anti-parallel, it's pretty strong because the hydrogen bonds are linear, right? Remember, linear hydrogen bonds are stronger than bent. And so, so here there's hydrogen bonding within sheets and London dispersion forces between sheets. And so here are our sheets, right? So this is anti-parallel. You can see here, this is coming towards us. This is away from us, towards us, away from us. And so these are, so between each other, there is hydrogen bonding. And between the sheets, there's a lot of van der Waals type interactions. So silk fibrin is one of the strongest proteins as well. All right, globular. So we have 10 to 15 minutes. So globular proteins. So here we have a variety of secondary structures. So first of all, now imagine if the globular proteins were only in one type of secondary structure. Let's say if it was beta conformation, then the length of these, so this particular one, which one is this? This is myoglobin, just 1 second. This is, which protein is this? Human serum albumin, so HSA, okay? So basically this is the predominant protein in the bloodstream, right? Human serum albumin. It's the protein that interacts with all these small molecules and drugs in the bloodstream. So if this only had one type of conformation, beta conformation, it would be super long, right? If it had alpha helix, again, super long and thick. But if it adopts this native globular form, where basically you have these alpha helices, now there are random coils between the alpha helices. Is this a beta sheet? Has to be, right? So if this adopts the globular form, then it's actually much more compact, and you can see 100 by 60 angstroms. So the protein is much more compact, and it allows for the hydrophobic residues to go inside the protein, hide away from water, and for the hydrophilic ones to become exposed to the aqueous layer. So specific arrangements, secondary structures. So we have alpha helixes, beta sheets, and boths. Now there is something called motifs, right? So for example, one type of motif, basically recurring structures in proteins. So this is a combination of various secondary structures. For example, yeah, the next slide. Let's look at the next slide. So this motif is beta alpha beta loop, right? So here we have a beta sheet interaction. Where is my? Then goes through alpha helix, comes back and forms a parallel beta sheet interaction, right? So we will call this beta alpha beta loop. So this is a very common motif within proteins. Another common motif is beta barrel, right? So here you can see it's made exclusively from the beta sheets, right? So these are anti-parallel beta sheets. So there's some random coil, turn around, going back, and so on and so forth. And it can form this kind of barrel-looking structure, right? So these are, so motifs, if you hear the word motif, sometimes called folds, basically these are combinations of secondary structures which are present in multiple proteins and very common throughout various protein families. So beta alpha beta, beta barrel is another one. Now here's another one. So beta alpha beta can also aggregate together with other beta alpha beta loops and form what's known as alpha beta barrel. Alpha beta barrel. So you can see here, if you look carefully, there's actually a nice binding site for drugs. So actually you can see here, there is a inside there's a hydrophobic
Can motifs be globular or fibrous?
motifs. Mostly they discussed in the term in the context of globular proteins, just because those adopt a number of different secondary structures, and so fibrous they usually have one secondary structure, right? So, but it's possible there may be other fibrous proteins. Not what we cover. So, but in this class we'll talk about motifs in the context of globular proteins. Okay, so is there anything else I want to say about globular ones? Let me see. Now keep in mind again that all hydrophobic residues will be inside, all the hydrophilic ones on the outside, because they'll be interacting with water, right? So that's the very common phenomenon for all globular proteins. So motifs, folds, loops. Oh, I think that's pretty much it. That's what I want to say. I'll actually give you some pages to read to get some more information. But other than that, these are the basics of the globular proteins as far as what I want you to learn in this class. And in the remaining minutes, I want to talk about intrinsically disordered proteins. Okay, so some proteins or specific segments within proteins which lack definable structure. Okay, and so basically they compose of amino acids whose higher concentration forces less defined structures. So so lysine, arginine. So for example, these ones, you can see that, so charged amino acids, because I knew that. So charged amino acids would force intrinsically disordered regions. Let me look this up. Charged amino acids. Well, they'll be exposed on the outer surface of proteins, right? Okay, look this up. I'm going to put this in a discussion. This is a note for myself. But this is very common, that the charged amino acids will force these intrinsically disordered regions in proteins. And so basically, the reason for their existence is that they can conform to many different proteins, facilitate interaction with numerous different protein partners, right? So they become promiscuous. So that's a very good one. Promiscuous. So they lose specificity, right? So they don't interact with just one protein, but interact with multiple proteins. For example, there is a protein P27, which is known as a tumor suppressor. Tumor suppressor protein. Basically what it does, it so basically it wraps around, so because it's has this intrinsically disordered nature, it's promiscuous, it can wrap around various enzymes known as protein kinases. So we talked about that. Protein kinases, which are involved in cell division. And so what happens if this wraps around a kinase involved in cell division? What's the net result? If you wrap around something, what will happen to this something?
It prohibits the process of cell division.
Yeah, it inhibits it. That's correct. Wraps around protein kinases involved in cell division. And inhibits cell division. In fact, it has been shown that many tumors do not express enough of this tumor suppressor protein. So one way tumors avoid this kind of process is by suppressing the expression of P27, right? In fact, the poor expression of P27. So cancer patients who have that, unfortunately, they get poor prognosis. Poor prognosis. So the cancers are unstoppable. Now there's another tumor suppressor protein known as P53. Okay, so this is P53. It's not shown here, but another tumor suppressor protein involved in cell division. So you can see here there is a what's Ponder score? I think that's it's hydrophobicity score. Just 1 second. Oh, disorder. Hold on a second. Yeah, predictor. So you will. It's in your notebook. So predictor of natural disordered regions. Okay. So, so you can see here in the carboxyl terminus, there's actually there are different conformations which can be adopted by the carboxyl terminus, and depending on this conformation, so it's not one frozen conformation, right? Not one specific conformation. It's a bunch of them. And so P53 can interact with a variety of proteins. So let's say if the carboxyl terminus adopts this kind of conformation, it will interact with cyclin A. This sirtuin, this CBP bromodomain, this protein, right? So so this is like a chameleon, right? Basically, it can change its conformation based on which protein it's interacting with. So P53 is a very smart protein, and that's why it's at the heart of regulation of tumor growth. All right, are there any questions about anything we've said today? So we will talk about X-ray crystallography and NMR, and we'll talk about protein folding on Monday. Any questions as far as today?
I have a quick question. On the slide before for the less defined structures, is that only those 4 amino acids, or is it all the charged amino acids? So like aspartate's not on there, or histidine.
Yeah, charged ones. Yeah, charged amino acids.
So not just those 4, all of them.
Yeah, I just remember that, but I don't remember the reason. I knew the reason, but I'll look it up and I'll put this in the discussion. Read the discussion, please.
Okay, thank you.
Mm-hmm. Anything else? All right. So have a good weekend. Stay safe. Wear masks. Wash your hands. And hopefully I'll see you all healthy and in good spirits on Monday.
Thank you.
Yeah. Bye, everybody.
Thanks. Bye.
Thank you.